All right, so 6-1. Functional composition. Like I said, the book titles this composite functions, but I prefer that language. So we're going to take a step back for a second and talk about functions. When we first started, addressing what a function is, we need to kind of revisit that a little bit before we can move ahead. So recall that when we talked about a function, something like y equals f of x, we first started with this idea of like a domain, which was like some blob of, let's say, numbers. This was called our domain. Those things got plugged into this machine, which we called f, which was our function. The function did something to that number, spit it out over here into what was called the range. And this was also a set of numbers, right? So a number went in, the function does something to it, spits a number out. And depending on the function that's given, that will dictate not only what's allowed to be plugged in, but what actually comes out. So for example, if I give you something like, let's say, x squared is our function, then what can you plug in to x squared? Do you have any domain restrictions? Can you, negative infinity, so all real numbers, right? When you want to square a number, there's no restriction on that, right? So we can plug anything we want in here, and then what would come out would not be everything, but just what? Positive numbers and 0, right? 0 can come out of that also, but it's impossible to get negative numbers out, right? Okay, so y'all remember this, yes? A little bit? All right. And then we, things like square root of x, well there, we had a domain restriction. You couldn't plug in negatives into this, right? And so we would have to, say something like 0 to infinity would be our domain, and then the range would be just positive numbers again, and then 0. So we can go through this and go back in our notes and take a look at that if we want. But just the idea of domain goes in, range is what comes out. So today, what we're going to do is we're going to talk about a fifth operation on functions, something we haven't discussed yet. So I'm still making you recall this. Do you remember that if you were given two functions, f and g, we define these things? Remember that? That notation meant, hey, we just want to add the two functions together, right? If we did something like this, that meant subtract the functions. There was another one. If we just wrote f, g inside the parentheses with an x, that meant to do what to the function? Multiply them. And then lastly, f over g would be division, right? These four operations are called our four arithmetic or arithmetic operations, right? Just like what we grew up using when we were, kids. You add, you subtract, you multiply, you divide, right? So if we start with two functions, right now we know how to do those four things with two functions, right? Today is all about a fifth operation that you cannot do with numbers. You can only do with functions. Let me try and illustrate that more. If I give you two numbers, right? If I give you two numbers, let's say the two numbers are, I'm going to go to a new page. If you're given two numbers, 5 and -3, it makes perfect sense for me to say add those together, right? I could say subtract the two. I could say multiply. I'll use a dot for multiplication. And then I could use division, right? Those four operations make perfect sense with two numbers. given two functions, same thing. I'll give you two functions, x squared, and then let's say x plus 1. Then I could add them, subtract them, multiply them, and divide them. Yes? Okay. So today's fifth operation, what I was just saying, the fifth operation, you can do it if someone gives you two functions, but you cannot do it if someone gives you two numbers. The operation makes no sense. All right? So it's something that you don't see as you are growing up, this fifth operation. And it is called functional composition. All right, so a fifth operation. Today is about a fifth operation called, we'll just call it, well, functional composition, or just composition. But, what did I just say? There's one stipulation in composition. You can only use it when you have two functions, right? But it only makes sense to use it when you are given two functions. Two functions. Right? Like if I said right now, what's 5 composed with 3? You would have no idea what to do, right? And you can't do it. You can only do composition when you have the two functions. So how is this going to work? I'm going to start with the visual, okay? And then from there we'll get into the notation. So first the visualization of this. I'll make this my next note, 6.1 point. Oh, actually make it 2. Let's go back and make that everything I just said when I said recall. Let's call this 6.1.1. All right, so here we go. Here's a visual, the visual idea of composition. All right, so what we're going to do is we're going to start with a domain, which again I'm going to say are numbers. I'm going to pass the number through to a function which I will call g. That g is going to spit out a number, isn't it? Yes? Okay. So it's going to spit out some number over here. This will be the range of g. With me? Okay. We're not done because composition has two functions. So what you're going to do now is this range of g is now going to become the domain of f, and we're going to take those answers and pass them through the f function, and then that comes out as the range of f, doesn't it? So what happens with composition is you have almost like a chain. Remember when I talked about functions, I talked about a car wash, right? Do y'all remember that? Okay. This is almost like if you ever go get your car washed at, like, what's that place called? Wash Tub or something like that. They offer you to like vacuum your car out first, right? And then after that they wash it. So this would be like the vacuuming stage is that first function. Your car comes out vacuumed. And then after that, you go through another function, which would be the cleaning. And maybe there's a third function, which is, you know, the waxing and detailing, whatever. You could have more than two. Now, we're going to start with just two. But as you move into calculus, you can have composition of, you know, up to, I don't think we ever go past like 5. But theoretically, you can have as many compositions as you want. The chain can keep going. Okay, so let's talk a little bit about this, because this picture will hopefully lead you to think about some things that might potentially become a problem. All right? Let's say that, let's try and do it without an example of a function. We know that there are certain numbers that we may or may not be able to plug into G, right? So G may have some domain restrictions on it. I may not be able to plug in 2, let's say. Or maybe I can't plug negative numbers in. Something, G is going to tell us there's something I can or cannot plug into it, right? All right, so that's going to go through whatever does go through. Okay, so whatever cars are allowed to go and get vacuumed, those come out the other side here. Now, those things that come out the other side are now going to try and go through F, right? F might have domain restrictions, right? But the restrictions we have on F are not dictated by this number. It's dictated by this, by what's coming out of G. So the range of G becoming the domain of F is going to cause a problem for us. And we're going to have to pay attention to it. And that's going to be one of these little subtleties that students are going to get hung up on, all right? Does that make sense in the chain of things, though? Okay, so let's take an example. Wondering if we should do some notation first. Yeah, let's just work on some notation. That's the visual, 6.1.2. Notation. So how do I tell you I want you to do composition? How do I actually let you know? Well, here's what we do. We write F with a little o in between it, like that. So this is not a multiplication dot. It's not an addition symbol. It's not a subtraction symbol. It is a little o. And it really stands for like of. Here's how we would say this. If you were reading this, out from a piece of paper, you'd say F of G of X. That's how you say this. F of G of X. Right? If that G wasn't there, right? If that little O and that little G wasn't there, you would say F of X, wouldn't you? You'd say F of X. But now what we're going to say is F of G of X. So looking at this chain of events, what I want you to see is that I'm going to highlight it. Somewhere in here, in this domain, right, lives some value that I'm going to plug in, which I'm going to call X. That X gets passed through the G function, comes out somewhere over here, and its value is G of X, isn't it? And then that value gets passed through the F function and comes out here. And how do I write that? Well, F with what? What got plugged into F? G of X. So we write G of X. Do y'all see that? That's terrible. That says F, and inside of F is G of X. Make sense? This right here, this notation, is telling you as a reader that you want to do this chain. So the definition of this is equal to, look what I'm going to write here, is F with G of X inside. That is the definition of functional composition. That's the notation we use. Now, I know that there are some teachers, and you may have heard this in the past, that call this fog. Y'all ever heard that before? Fog? Fog X, whatever. I'm not a real big fan of that, only because it makes students think that fog is the only thing they can ever have. You can flip the order, and you can also have G of F of X, which would be, how do you think that would change our chain? If instead of doing F of G of X, I did G of F of X. How do you think this would change? Yeah, the F would go here and the G would go here. So what would happen is F would get that input first, then spit something out, and then G would get that answer and spit that out. And then there's nothing that stops you from doing something like F of X, where it's like you send something through F, that answer comes back out, goes through f again. It's like you vacuum it, nope, go vacuum it again. Like it can happen where you can have a chain of the same function with itself. And then you could do it 3 times. So you could have, yeah, you could have fofuff, or you could have goffuff. I mean, you could have f of g, you could have g of f, you could have f of g. I mean, all these different combinations, right? And that's only 3. You could have 4 functions. You go f of g of f. Yeah, so you get the idea. It can become kind of, you know, there's no restriction on what it can be. So why tell students fog? That's only one example. So, all right. So here we go. Y'all with me? Okay, so let's start with an example that's pretty clean, that's going to give us no domain problems. All right? So here's our first example, 6.1.3. Given f of x equals 4x plus 1 and g of x equals 3x squared, find f of g of x and its domain. What's that? It could, but it would be really bad notation to do that. To call a function x of x, like that, that would just be bad notation. If anything, make it a capital X of little x. It would be confusing, right? Okay. All right, so let's just grind this thing out. I'm going to first draw a quick picture of showing what's happening. And when I say quick picture, this is what I mean. X is going in. It goes into G first, right? Comes out as G of X. That now goes into what? The F function, and comes out as F of G of X. So I will highlight, these are the machine parts, right? This is the domain of G, goes in, comes out as G of X. That's now the domain of F, goes in, comes out as F of G of X. Do y'all see that? It's this picture without all the cute little, you know, blobby things around them, right? Okay, so let's do the composition. Let's actually do this, and then we'll come back and look at the domain, all right? So here we go. F of G of X, by its definition, is equal to F, and inside of it, G of X. So watch how I write this. This equals F. Now tell me, what is G of X? Whoa, what happened? This right here is 3x squared, right? That was given to me in the problem? Yes? So I'm just going to replace it right now with 3x squared. Now, tell me what the f function is going to do with this. So let's go back up and look at f. Here's f. We are going to, see, this is our f. This is the thing that's getting put in. Here's the thing that's getting put in, right? So we're going to replace this x, right, with 3x squared. So I'm going to rewrite f right here, but instead of writing x, I'm going to write this. So it'll look like this. 4, and then I'm replacing the x with 3x squared, and then the rest of f was what? Plus 1. So notice the f goes away here, right? Because I'm actually plugging this into the function f, so there's no need to write f anymore. This is what f does. It's 4 times whatever you plug in plus 1. What's that? Question? You sure? Come on. Okay, well, let's go back up to f, and let's just wipe everything off the table for a second. Here's the function f. If I asked you to plug 1 into it, what would you do? Right here. You just replace that with 1, and that'd be at 4 times 1 plus 1. If I say plug in 2, you'd plug 2 in for x, right? If I say plug in t, you would just replace this x with t, right? And it would become 4t plus 1. You still, yes? What I'm asking you to plug in, though, is 3x squared. So I want you to come up here and I want you to replace that x with 3x squared, which is what I've done. You see it? Now just multiply this out. 12x squared plus 1. And we're done. We're done with finding what it is, 12x squared plus 1. Box it up. That is the composition of those two functions so far. Yes. Okay, any questions on that? Let's talk about domain. All right. So going to this picture, let's first look at G. Because G was the first one to work on this thing, right? G is the first one that got the X. Is there anything that you cannot plug into G? So let's look at G. Does G have any domain restrictions? No. So would you agree right here, negative infinity, do y'all see me squeezing this in here? Do y'all see that? I can plug anything I want in for X here. It's going to spit out something, right? It's going to spit out something over here. Now, let's look at F. Are there any domain restrictions on F? This thing right here has no domain restrictions, right? So no matter what comes out of G, F will be able to handle it, won't it? No matter what. So I'm going to put here negative infinity to infinity is what can go into F. I'm just trying to give you some sort of visual guide as to what's happening here. Since these both have no restrictions, this right here, the composition has no restrictions. And so the domain of the composition, the domain of f of g of x is negative infinity to infinity. Yeah, well, we're going to see, that's the tricky part. Let me get to it, all right? Let's go a little slower with it. All right, we good? That's it. That problem would be done at that point. Sure there's no questions? All right, next example. Let's do the same two functions. Ooh. Given f of x is 4x plus 1, and g of x was 3x squared. Find g of f of x and domain. So what's the difference here? I wrote g of f of x instead of f of g of x, right? So I switched the order of f and g. I'm going to what? X is going to go into... Yes, that's what's going to happen. Let's write it out, though. I'm going to first start by rewriting what this is. By its definition, this is g on the outside. What goes into g? F of x. Okay, that's the definition of g of f of x. Now let's rewrite that. Don't touch the g, but replace f of x with what it is. So what is the f of x here? 4x plus 1, right? I think I'll do that in red. Okay, that's what f of x is. Now, again, you see what's going to happen here? G is going to get fed this. So here's G. It's sitting there. It's waiting to be fed something. Whatever we feed it, it's going to go right here. So what will my next line be? Now hold on, no one answer. I'm going to put you all on the spot. Come on, let's go for it. There's no. So let me ask you, do I write the G or no? No? Okay. So 3, right? Is that what you said? 3, hold on, parentheses, 4x plus 1 squared. Now hold on, let me put this in red. So all I did was I replaced this x in G with what I was giving it, right? I was handing it this, so it's going to replace that x with this. You'll see it? Now you have to clean this up, which means you have to, well, what do? Boil it out. You have to multiply this out first, which means you have to do 4x plus 1 times 4x plus 1, and then do this thing. So you have to do the expanding of this first, and then you get this. But what was sitting in front of all that? A 3. So my next line, I'm going to have 3 sitting in front of all of this. And then finally, pass the 3 through. 48x squared is 24x plus 3. Got it? Questions? Domain. Let's talk domain. Who got it first? So I think I'll draw my little picture on the side here. X went into what first here? Which function, f or g? Look at, here's x, right? What did x go into first? F, right? That went into f, gets spit out as f of x, then that gets plugged into what? G, and then gets spit out as g of f of x. Highlighting again, those are the functions. Domain, x goes into f, that spits out its range. That range now becomes the domain of g, that spits out g of f of x. Was there any restriction on the x getting plugged into f? No, going back up to f, that's a line, domain is everything. So who cares what comes out of it, right? Well, we have to look at g now. Does g care what comes out? G can handle anything, can't it? So it can care less what it comes out. Yes? We're going to do it. That's our next example. All right, so there are no restrictions passing through this string of functions, right? So therefore, our domain here is all real numbers, everything. Yep, interval notation. Do you see why you can't do this with numbers? I gave you two numbers, 5 and 3. How do you plug 5 into 3 first? And that doesn't make any sense, right? All right, here's a very, very important example, all right? What am I on, 4 or 3 here? 5? Either one. Given f of x equals 1 over x minus 3, and g of x equals 4 over x plus 1. Find f of g of x and its domain. All right. Now, please pay attention, all right? Right now, forget the composition. Just think about this for a second. Is there a domain restriction on F? Is there something I cannot plug into F? I can't plug 3 in, right? F cannot handle 3. So that would be a restriction, right? Like everything except 3.
Is it 3 or -3?
It's 3 here. Because if I try and plug 3 in, 3 minus 3 would be 0. -3 minus 3 would be -6. That's okay. So I could not plug 3 into F. Agreed? Okay. What about G? I can't plug -1 in, right? So you would think right now, for sure, we can't have 3 and -1 ever, right? That's what you might think. It's not going to turn out that way. All right? It's not. So that's why I said this is tricky. So I think what I'll start off with first is let's just go and find what is f of g of x. Let's do that first, then we go visit the domain. All right? So the first thing I'm doing is rewriting this is f with g inside. How are you going to remember which one goes inside when I give you f of g of x versus the other way around? How do you remember it? Yeah, the first one's on the outside, right? The f is on the outside. The g is closest to the x. That's the one that's on the inside. All right, that's the way you can remember it. All right, let's replace the g with what g is given to be in the problem. What is g given to be? 4 over x plus 1. So that's going to go right over here. 4 over x plus 1. We are about to feed the f function this, right? The f function takes whatever it's given and it sticks it right down here, doesn't it? So I'm going to rewrite this entire thing. I'm going to replace this x with that entire ugly, nasty looking thing, right? That's what's going to happen. And we are going to end up with a complex fraction. So I start with the 1 on top. I replace the x with what? 4 over x plus 1. And then what do I still have there? Minus 3. Does everybody see that this is the f function with the x replaced with g? Yes? Okay, unfortunately, we are not done. That is unacceptable as a final answer on a test, and this is what's going to make this even harder. We haven't even talked about domain yet. That's what's going to make this even harder. We have to clean that up. That is not an acceptable expression when you move on to a calculus class. That must be simplified. So this is the class that we learn to simplify this and get good at it. So we have what's called a complex fraction here. It's a fraction, right? A big fraction, 1 over something. But in the denominator, we have a fraction minus a number. So what I'm going to do first is I'm going to start by cleaning up the bottom. I'm going to take a look at this right here, and I'm going to try and put those two together. How can you put two things together like that? You need a common denominator. So how about I do this on the side here? I'm trying to do 4 over x plus 1 minus 3. Can I rewrite that 3 as 3 over 1? Yes? So I'm just rewriting the bottom over here. And you said I need a common denominator of what? X plus 1. So I introduce an x plus 1 on the top and an x plus 1 on the bottom. Yes? Now I can put these two together. Let me actually distribute the 3x through. I'm going to rewrite this whole thing. I have 4 over x plus 1 minus 3x plus 3 over x plus 1. Everyone agree with that? Now I can put them together because they have the same denominator. What do I need to be careful with, though? I'm doing this on the side here. I need to be careful with this negative in the middle, right? That negative needs to pass through to each of these. So what would we get on top if you do 4 and then take away that stuff? 4 minus 3x minus 3 over x plus 1. So now we put all this together, combine 4, take away 3, you get a 1. So you could either write this as 1 minus 3x, or you could write it as negative 3x plus 1. Either way, over x plus 1. Are we good or not? That's just this part right here, right? So let me come back here now and rewrite this. 1 over 1 minus 3x over x plus 1. That's what I said, yes. You could write minus 3x plus 1. It's the same thing. Okay, now I changed that division bar to a black division bar because I wanted you to notice that that's the main division we have. So what is 1 divided by a fraction? What can you do whenever you have 1 divided by a fraction? Yes. That's right. It flips. It flips up. Now, I want to show you why it flips up because a lot of people don't really understand what's happening here. All I'm doing is this. I'm multiplying the top and bottom by x plus 1. Okay? When I multiply the x plus 1 on top, x plus 1 times 1, what do I get? X plus 1. When I multiply this across the bottom here, these two cancel. So it's like this is on the top up here, and it cancels out. So all you're left with is the 1 minus 3x. This is your functional composition right there. Yes?
Going back to where you have the 4 minus 3x plus 3,
Mm-hmm.
couldn't you just switch, like, couldn't it be negative 3x plus 1?
Yes, yes. That's the same expression. You could do that. You could use this. Yep. I multiplied top and bottom by x plus 1. And over here on the bottom, it's kind of like I have, if I multiply 1/4 times 4, these 4's cancel, right? That's what would happen. So that's exactly what's happening here. But we had one on top also, so. Any questions on that algebra? So that is the composition, right? Y'all agree with that? Now, looking at this composition right now, let's start to talk about domain. There's a problem with the domain here, isn't there? It's possible that this could be 0, right? We'll have to figure it out, but this could be 0 here, and that could be a major issue. So we do have a problem with domain that we were not able to recognize by looking at these two, right? Up here it said 3 would work. Don't use 3 and don't use -1, right? But here, that's not what's going to cause the problem. Something else is going to cause the problem, isn't it? 1/3 is not going to be possible. But we couldn't see that from here. Okay, so y'all ready to talk about domain now? Yes? All right, here we go. Here's the domain part. I'm going to start a fresh page. For the domain, I think what I'll do is I will start by drawing our picture again. We had x. X goes into what function first? In this problem, it went into g first, right? That came out as g of x. That's not g. That g of x went into what function? F, and came out as f of g of x. I'm highlighting now. If you want, you can circle these. Those are just representations of the function. Okay. Now below this, because this one's more complicated, below this, here's what I'd like for you to write. X, when it goes through the g function here, right, it goes through g. What is the g function? What is it? Okay? Y'all with me there? That's what happens. When you plug x into g, this is what you get. Now, think, all right? This, whatever this answer is, cannot screw up f, right? F needs to be able to eat this and spit it out, right? What can't f handle? What can f not handle? So go back up here. F could not handle, F could not handle 3, right? F could not handle 3. Do y'all agree? So what I know is that this right here better not be equal to what? 3. So what I'm going to put here is this cannot equal 3, right? I need to make sure that what comes out of that can't be 3, because it'll mess F up. So if I want to know when something is not going to be equal to 3, then I need to go figure out what would make it 3 and pull that out and say it can't happen, cannot have that happen. So below this, let's actually try and figure out when this would occur. When would that actually take place? Do you understand what I'm doing here? X is going into G. I need to make sure that when G spits that answer out, it better not be 3 or F's going to freak out. So I'm going to go figure out when it's 3. When does the G function spit out 3? This is what we call a rational equation. Right, this is an equation. Just solve for X. How would you solve this for X? You multiply both sides by the LCD. How many of you took 320? Math 320. The one before this? Math 320, you spend a lot of time solving what are called rational equations. This is why. This is a rational equation. So we are going to find the least common denominator, which in this case is x plus 1. We're going to multiply both sides of it by the LCD. That has the effect of clearing the fractions out. Because what happens on the left side here? These cancel, right? So all that's left is what? 4. And then on this side, what's left? 3x plus 3. Now subtract 3 from both sides, and you get 1, and then you get 3x. And then divide through by 3, and you get x is 1/3. But remember, this is going to tell you what x can't be, right? Or else you're going to have an issue. So recapping, this little thing that I circled here tells us that if I start out with the 1/3 over here, right? If I try and plug a 1/3 in, when I plug 1/3 in, it's going to spit out a 3, and then F's not going to be able to handle it. So I need to take that 1/3 out of the domain. Is there anything else I need to take out of the domain? What about G itself? Is there anything that G couldn't handle plugging in? -1. Right? Look at the G function. Remember we said G couldn't handle -1? Since it's the first function getting something, it's got to be able to handle it. So I can't plug -1 into this either. So there are two things I have to pull out of this. I need to pull out a -1 because G can't handle that, and I also need to pull out a 1/3 because even though G can handle it, when you plug that into F through the composition, it won't be able to do it. I hope that makes sense. You always have to look at the original function, the first function in the chain. So I'm going to put here also x can't be -1 because G of -1 is undefined. We get division by 0. So what are the two numbers I pulled out? -1 and 3? Wait, where was it? 1/3. Where did I do it? Was that the next page? Oh, oops. I meant this to be on the next page. So here's our final answer, our domain. We said x cannot be -1 and x cannot be 1/3. Give me that in interval notation. -infinity to -1. Jump over -1 until you get to 1/3. Jump over jump over 1/3 and go to infinity. That's your domain. Everything up to -1, but not -1, and then everything up to 1/3, and then not 1/3, and everything on. Let's try something else. I want to give you at least one of these as an in-class, assignment today to work on together. Because watching me is one thing, doing it yourself is another. Let's try this. Given, this is 6.1.6. Given f of x equals 1 over x minus 2, find f of x and its domain. So let's find the actual functional composition first, then we'll go look at the domain. So f of f means you're going to start by taking f, and inside of it you're going to plug in what? F, right? That's what you're going to do. Start with f, plug in f. Rewrite this. That's f on the outside, haven't touched it. Replace f inside with what? 1 over x minus 2. Y'all follow? But then I'm going to take 1 over x minus 2 and plug it into f. So I'm going to be replacing this x with 1 over x minus 2. So this next line is going to look like this. 1 over what? 1 over x minus 2, but then minus 2. See how that worked? That's what happens when you take 1 over x minus 2 and plug it into 1 over x minus 2. You get 1 over whatever. You see what you get. So get a common denominator between these two. So I'll do that. I'm going to try and write this all in one line without actually having to do scratch work on the side. Rewriting this is 1 over x minus 2. I'm going to rewrite the 2 as 2x minus 2 over x minus 2. So I introduce next to this 2 on the top and bottom an x minus 2 so that these would have the same denominators. Then I have what? I'll go a little bit slower, but yes, minus 2x. So 1 will take away 2x, right? But then minus a minus would be a plus, and that would be 2 times 2 would be 4. So we should have 1 minus 2x plus 4 over our common denominator, which was x minus 2. Which is the same as 1 over 3 minus 2x over x minus 2. Not 3. It's 5 minus 2x. Yeah, you have 1 plus 4. See this negative sign here? Maybe it's too much. These together is 2x minus 4. But then you have the negative sign that must go through and change both of those to a negative 2x and a plus 4. Then the one that was in front out here. So you have 1, the minus 2x, and the plus 4. 1 plus 4 is 5. Take away 2x. We good? All that really winds up happening now is this fraction flips over. Okay. Questions on finding f of x? Domain time? Okay, so x is going to get plugged in. It goes, let's try this a little bit different now. X is going to go into f. What does f spit out? Which is? It's 1 over x minus 2. That's going to get plugged into f again, right? And when it does, it's going to come out as our answer. Isn't it? You see how I've done this? Initially, it starts out as x. It goes through f. It comes out this. We already know it's going to come out at the end to be this. But what is it? What is it that this x that could not go into f? What do we have to get rid of to start off? 2, right? 2 couldn't come in here. So this right here tells us x can't be 2. Right? We couldn't plug 2 into the original function. And then whatever comes out here, this piece is going to have to go into f again, right? That means this cannot be what? What can't f handle? What can f not handle? No. What could f not handle here? 2, right? This is what comes out the first chain. We need to make sure this cannot equal 2 also, right? Initially, whatever we plug in can't be 2 because f wouldn't be able to handle it. That output that comes out can't be 2 again because it's got to go back into f. So this can't be 2. That's right. The function cannot be 2. So let's see if we can figure out where this happens. So I multiply both sides by what here? X minus 2, which would leave me with this, which gives me 1 equals 2x minus 4. 5 equals 2. 5 halves equals x. So right here, this is telling us what x can't be, right? I think I know what you're going to ask me. You could do that from here?
Yeah, but would that ever change anything?
That can be dangerous later. Yep. Yeah. Yeah. Especially if you have your chain is more than 2 functions.
So, just, I guess to make it simpler, whatever the first function is that you have to take out, the first number that you have to take out, you just have to make the second function
equal that and figure out, well, if it's the same function, right? Because, yeah, if this was a different function like g, we would have to say, well, what can g not handle? 10, let's say, it can't handle 10, then I would set this equal to 10 and figure out when that happens. All right, so give me my domain. What can x not be? Can't be 2, and x can't be 5 halves, right? So let's make sure we get this right. It's going to be negative infinity to 2 union 2 to 5 halves union 5 halves to infinity. There it is. Everything except 2 and 5 halves. Okay, let's do one more. I'm gonna go for broke here. I don't know. Might have to do 2 more. Right? I want you to be able to do your homework. As much as I want you to do some work in class, I'd like to expose you to some more. Let's say we have f of x is the square root of x minus 2. And let's say g of x is 1 minus 2x. Let's find the domain, or find f of g of x and its domain. Okay, here we go. So let's try, write this down, it's f of g of x. I replace the g with 1 minus 2x, right? Then I feed that into the f function. That means that this x gets replaced with 1 minus 2x. So it's going to be square root of, here's the 1 minus 2x being fed in, but what's still in there? Minus 2, which is equal to the square root of what? Negative 2x minus 1. Or you could write negative 1 minus 2x, either way. Okay, that's our composition. Now let's talk about our domain. X is going to go into what function first? G. And when it goes through G, it comes out as 1 minus 2x. Then that answer is going to go through the f function. It's going to come out as square root of negative 2x plus, minus 1. Let's talk about this first loop here, the first chain, piece of the chain. When x goes in here to G, is there any restriction? No, because G, the domain is everything, right? Domain of this is everything. You can plug anything you want in this, no problems. No division by 0, no square roots. So, no problemo. No problemo there, right? We're good to go. Now, this is what comes out, right? This, well, no, you can have 2 because what's 2 minus 2? 0 square root 0 is okay. What is it? Yes, well, what can't be negative? Everything here can't be negative, right? So this is, see, this is much trickier than the other one. Watch. I'm going to insert some space up here. Look, if I asked you right now, what was the domain of this, you would say domain of that was what? All real numbers. If I asked you what's the domain of this one, you would actually have to say, well, the x minus 2 must be greater than or equal to 0. This is how we did domains when you had square roots. We looked under the root and we said, hey, that has to be positive or 0, which means that this would have to be, x would have to be greater than or equal to 2. Agreed? Yes? So what we need to see here is that when we're going in this step, when this is going from here into here, we need to be sure that the 1 minus 2x is what? Greater than or equal to 2. Because that's what f can handle, right? F can handle whenever this thing inside, whatever it is greater than or equal to 2. So we put here greater than or equal to 2. And now we solve this. So how about I subtract 1 on both sides? Is that all right with you? This is what we call linear inequality. I'm moving 1 over to this side by subtracting it. So I've got this. Then what? Divide by negative 2. Any issues there? Anybody remember what happens to an inequality symbol when you divide or multiply both sides by a negative number? It flips. Y'all remember that or not? Okay. If you forget that, it's wrong. Huh? What's that? Oh. When you multiply or divide an inequality by a negative number, the inequality symbol flips over. So this is going to become now, the left side is x, but instead of greater than or equal to, it's less than or equal to negative 1/2. Flip. Every time I get to that, I think of flip. I think of that movie, The Usual Suspects. Y'all seen that? Usual Suspects. Show of hands. Usual Suspects. Really? Seriously? The guys with all the guys in the lineup. That's the front cover of like the movie thing. No? Oh my gosh, you're missing it. It's a good movie. Anyway, yeah, Kevin Spacey, when they're interviewing that one guy, he's like, they'll flip you. All right, never mind. Okay. Go watch it. Extra credit. Yeah, it's good. It's good. I'll ask a bonus question on the next test based on that movie. How about that? Sounds good. All right. So, let's see. What is our domain then? What's our final domain here? We said no problems here, but here x has to maintain this inequality. So this is our domain. X has to be less than or equal to negative 1/2. So how do I write that? Negative infinity to negative 1/2. And then bracket, because it's equal. Okay, let's just check, because this seems a little weird. What you're telling me is that I can't plug 0 in? That's what you're telling me? I can't plug 0 in, or else this thing's going to fall apart? All right, let's try it. Try and plug 0 into our answer right here. What would you get? You get negative 1. Square root of negative 1? Well, we've put the I away now. Okay, we used the I for a while, but now it's put away again. Why, remember I was trying to tell you that's why I don't like showing it to people, because it's, yeah. Okay, so that makes us feel better. If we're saying, hey, look, you can't have 0 in there, and we plug 0 in, we have a problem, we're feeling good about our answer. Mm-hmm. Yeah. Okay, one more. I've got, what, another 25 minutes? You would have to solve a linear inequality or rational inequality. Hmm? Well, I'd have to see that second function. I can't say. I'd have to have the function to make sure. It's not going to be like a general rule of thumb that it's always this.
Well, like let's say if what you had to take out of that function that we had was a positive number.
Okay, you mean like the original one? Okay, so what you're saying is, let's say we had a problem here where it said x couldn't be 2. But down here we got this. We would not have to include that in our answer, because that already says x can't be 2. That's right. Less than, exactly, yes. Okay, last hopefully example, we'll see. 6.1.8. Functions are starting to look a little more complicated, aren't they? All right, so let's write this down. We have f, and inside of that goes g, which means we're going to have f, and inside of that goes, well, g, which is x plus 4 over 2x minus 5. Uh-oh. So then So then this gets replaced, fed into F, and it's going to replace every X that I see in F, meaning both of these. So it's going to become, no more F, it's going to become 2 times what? X plus 4 over X minus 5, okay? 2X minus 5. Then minus 1 up there still, right? All over X plus 4 over 2X minus 5. Ooh, minus 2. Give me a quick second. Is the sun breaking out? No? Not really, huh? Start warming it up. Yeah, that's a nice mess, isn't it? Okay, let's work on this now. So I'm going to distribute the 2 through to this, right, first? To get rid of the parentheses here, which means it goes to the top or the bottom or both? Top only. That's like a 2 over 1. So it's going to become 2x plus 8 over 2x minus 5 minus 1 over x plus 4 over 2x minus 5 minus 2. Now, we have 2 sets of complex fractions. So these up here, I'm going to put these 2 together. I'm going to put these 2 together, which means I need to get common denominators. So see if you follow this. 2x plus 8 over 2x minus 5 minus 1 times 2x minus 5 over 2x minus 5. Yeah, we're going to do it. Well, I'm doing them all at one time, but
Why does the 2 only multiply the
yes. You're talking about this 2 right here? Because that 2 is like a 2 over 1. And so you're multiplying 2 fractions here. A fraction times a fraction. When you multiply fractions, you go straight across. The 2 goes across, and then the 1 goes across the bottom. So it's just the top. Okay, so what did I do here? This 1, I needed to get a 2x minus 5 on the bottom, so I multiplied 2x minus 5 on top and bottom, and that's this. This 2, I needed a 2x minus 5 on top and bottom, so I put it there next to a 2. And now I get to put all this together. This is exciting. Yep. All right, so 2x plus 8 minus 2x plus 5 over 2x minus 5 all over x plus 4 minus 4x, what's that, plus 10 all over 2x minus 5. What did I do? What happened here? Negative 2x, positive 10, right? Distributed the negative through here. Negative 2x, positive 10, right there. Or negative 4x, sorry. Negative 4x, positive 10. Did I say 10 just a second ago? This goes through negative 2x plus 5, negative 4x plus 10. Let's clean up those numerators here. 2x, hey, take away 2x. Are they gone? So 13 over 2x minus 5 over negative 3x plus 14 over 2x minus 5. Remember, our big division bar is right here. So we flip that fraction up, and the 2x minus 5s are going to cancel. So I'm going to write down next to this what happened. The 2x minus 5, we flipped it up. Okay, it's gone here. So I flip it up like this. And then these 2x minus 5s cancel. disaster, which is, yes. Okay, this, we said a fraction over a fraction is the same as flipping it up. So I flipped it up, so this is not here, it's now here. And then I noticed that 2x minus 5 and 2x minus 5 are the same, so I canceled those. Got it? So what's left is a 13 on top and negative 3x plus 14 on the bottom. That is my composition. Now domain. So let me get to the domain. I think the best thing is for us to go just revisit F and G by themselves at the top. What was the domain restriction on F? X could not be 2, right? What about the domain restriction on G? X could not be 5 halves positive, right? So what I'm doing is I'm saying this one, I'm just saying, hey, look, 2 minus 2 is 0. That's a problem. So I can't have 2 in there. This one, you actually have to take 2x minus 5 and set it equal to 0. You're asking yourself, when's that 0? And then you move the 5 over and divide by 2. So I know right now I cannot feed G 5 halves, and I can't feed F 2. Yes? Okay. Let's try and get domain now. Our X is going through G first. When we go through G, it comes out as x plus 4 over 2x minus 5, yeah? Is that what G was? And then that gets fed through F, and we got our answer to come out to be 13 over, what was it? Negative 3x plus 14. Okay? We knew going in here, what could we not feed G? G couldn't get 5 halves. So x can't be 5 halves. What can this not be equal to? So we're trying to feed F right now. This thing right here, x plus 4 over 2x minus 5, cannot be what? Was it 2 or negative 2? It was 2. F can't handle 2. So this cannot be equal to 2. So I'm going to have to figure out when it is 2. So let me figure out when it's 2. X plus 4 over 2x minus 5 equals 2, which means x plus 4 equals, I'm multiplying both sides by 2x minus 5. 4x minus 10. So solve this equation for x. So move all your x's to one side, all your numbers to the other. 14 equals 3x. So 14 thirds is x. That's what it can't be, right? So my final domain, I said x could not be 5 halves, and x could not be, what? 14 thirds. Which is interval notation, negative infinity to 5 halves, union 5 halves to 14 thirds, union 14 thirds to infinity. Yes. Bless you. These have to be in the correct order. How do you know? I know that 5 halves is smaller than this. I'm thinking about it. 5 divided by 2 is about 2 point something, 2.5. 5 goes into, 2 goes into 5 how many times? Like 2 or so times? How many times does 3 go into 14? Like 3 goes into 12 4 times, right? So I'm doing it that way. But that's a side note. If I give you any two fractions, how can you see which one's bigger? There's an easy way. There's a real easy way. All you do is this. You multiply these two numbers right here, you get 15. You multiply these two numbers right here, you get 28. 28's bigger, that means this fraction was bigger. You can do that for any two fractions.
But what if, like, the other one that we did, it was 2 and 5 halves, and we put 2 first?
It was 2 and 5 on this one?
Yes. No, the other one.
I was there. Which example?
What f of x, f of x.
The f of f one?
Yeah.
Oh, there. Oh, I didn't see it over here. Okay, which of these is bigger?
Yeah.
5 halves is 2.5. 2.5 is to the right of 2.
Okay.
Yes? Okay, so we're not going to be able to, I still need to give you your homework assignment. I'm going to kind of trim down what's in here. Just follow me real quick. Don't write this down. Certain dangers you run into. If I had f of x was square root of x, I had g of x. Oh, you know what? Let's do it the other way. F of x is x squared. G of x is square root of x. Then if I said find f of g of x, you would plug g into f, right? That's g into f. And that means you would replace this x with square root. So it'd be the square root of x squared, which is just x, right? So if you look at this final answer, you may think, hey, there's no domain restriction at all, right? But there is, because when I go x goes into g first, it's square root of x, then goes through f, and it comes out we just said was x, right? But we have a restriction going in here, don't we? G can't handle negative numbers. X must be greater than or equal to 0. From here to here, it doesn't matter. No problem, because I'm squaring something, right? F is going to square something. There's no problem. So the domain here is x is greater than or equal to 0. You would not be able to see that from just looking at the final result. And earlier, I don't know, some of you picked up on this, that the final result, like this right here, remember we could say when is that 0 is 5 halves. We could have picked up that 5 halves here, but I made you go back and do it this way. It's because with other problems like this one, you can lose the domain restriction within the algebra. Okay, homework. This is an extremely important homework assignment, all right? So make sure you attempt the problems. I'm trimming down, so don't do what's on the schedule. I'm going to just do a subset of it. So let's do, where is it? 31. So 31, 37, 41, 43. $45. I'm going to circle that one. I haven't done that yet. That's just an interesting problem. See what you do with it. This is page 407. Yeah. Yes. Pay attention though, because for each of these problems, I believe they ask you to do f of g of x, and g of f of x, and f of x. So each one of these is like 3 problems, I think. And for each one, it's find the function in the domain. Just those 5 problems, yep. So look, like I said, very important, the algebra involved in this, the little things, simplifying fractions, that's critical. So practice it in the homework, come with questions, expect a quiz. and have a good day.